All right, so we're now ready to make the behavior of a Markov chains for in the long run more precise. So definition for 3.5.3, steady state and regular transition matrices. A probability vector Q is a steady state of P if P, Q equals Q. So two things we need. We need to be a probability vector, so the sum of its entries should be 1, and we need it to stay put when you multiply it by P. A transition matrix P is regular if either P or some power Pn have only non-zero entries. All right, so note that a steady state is an eigenvector of P with eigenvalue lambda equals 1, right? P of Q equals 1 of Q. It also needs to have entries that sum up to 1. All right, so here's the theorem. Let P be a regular transition matrix, then there is a unique steady state Q for P. For any initial probability vector, x0, limit of xn is going to be Q. So wherever you start, you'll end up at that steady state Q. And then if you take the limit of the P to the n, that's our Q matrix from the last problem, sorry, each column will be Q. Right, so that matches what we have. This is our steady state because we checked that PQ equals Q. If you look at the Q matrix, the columns are 2 over 5, 3 over 5. And if you take any x0, if you take the limit, if you take xn, you'll end up with Q. All right? So let's test a few things. So example 3.5.4, are the following matrices regular? If so, find the unique steady state for P. Right? So I need to check if P or powers of P have only non-zero entries. All right, so let's try with this one. So if I do P squared, sorry, I get 1, 0, 0, 1, I get the identity. Still has 0 entries. If I do P cube, that's going to be B plus times P squared. P squared is the identity, and so I'm just going to get P. And so really, P to the n is either P, which is 0, 1, 1, 0, or I, which is 1, 0, 0, 1. In any case, it has 0 entries. So we don't have a regular transition matrix.